Now we're going to put everything together into conservation of energy problems. As always, if you enjoy this content, please like and subscribe. So when we talk about any conservation law, what we're saying is that the total amount of something isn't changed, it's conserved. So if we're going to conserve energy, then the total energy that we start with has to be staying the same the entire time, no matter what happens. So another way to say this is the sigma or summation sign. By summing up all of the energy that we start with, that's going to be equal to the sum of all of the energy we end with. Now, a very complicated version of writing this out would be to say all of the PEG, the PES, and the KE initial has to be equal to all the PEG, PES, KE final, plus whatever heat is produced, if there's any heat produced. But in almost every situation, we're not going to have all of these forms of energy. So most of these will drop out to zero, but we'll still have an equivalence. So I'll give you an example of a problem like that. Let's say we have a toy gun that has a spring in it, and when the spring goes off, it shoots the ball out of the little toy gun. And let's say that the spring has a spring constant of 100 newtons per meter, the spring gets compressed 0.2 meters, and the mass of the ball is 0.15 kilograms. So what is the sum of all the energy that we start with? Well, we only start with one form of energy. We start with PES. And when the spring becomes uncompressed, the PES becomes zero, and all of the energy goes into the kinetic energy of the ball. So that becomes KE. So this is our sum of the energy we start with, and our sum of the energy that we end with. Now we can put in our formulas. 1/2 kx squared must equal 1/2 mv squared. So we know that K is 100 newtons per meter, so we have 100 newtons per meter, and x we said was 0.2 meters. We're going to square that, equals 1/2 times 0.15 kilograms for the ball, and we're solving for how fast the ball will come out of the barrel. And when you do the math on that, you end up with v equals 5.2 meters per second. Now, that's a pretty common question to get asked, but also, they may ask you to do this as a derivation. So if we were to do this as a derivation, we would start the same way. We would say all the spring energy turns into kinetic. We would do 1/2 kx squared turns into 1/2 mv squared, and then we're going to solve for v. Well, we can cross out the halves because we have halves on both sides, and we can bring the m over to the other side and take the square root of both sides. So that's going to give us v is equal to the square root of x, because the x comes out because it's squared under the root sign, over k over m. And if you put these numbers into here, you'll get the same answer. So let's switch the problem up a little bit. Let's say that now we take the gun, and instead of firing it sideways, we fire it straight up. And the question is, how high is it going to go? So in this case, the energy starts as PES, and it ends over here as PEG. So again, our concept is the total energy we start with has to equal the total energy that we end with. So that's going to be 1/2 kx squared is equal to mgh, and we're going to use the same numbers that we used before. We had 100 newtons per meter for K, and the x was 0.2 meters. We have to square that, is equal to 0.15 kilograms times 9.8 meters per second squared times the height. And when you do the math on that, you get 1.4 meters. What if we were asked to do this as a derivation? Again, we would do the same thing to start. We would say 1/2 kx squared equals mgh. We're solving for h, so we would divide through by mg, and that would give us h is equal to kx squared over 2mg. Let's look at another problem where we have a block that starts from rest, it's dropped, and it falls down a distance of 60 meters, and right before it hits the ground, it's going very fast. And if there's no air friction, how fast is it going just before it hits the ground? Well, let's look in terms of energy. All of the energy that we start with is right here, so that is PEG. And then right before it hits the ground, all of that PEG turns into KE. So we have mgh equals 1/2 mv squared. And what's nice here is that mass is on both sides of the equation. So we don't actually have to know that 2 kilograms. So we have 9.8 meters per second squared times a height of 60 meters is equal to 1/2 times v squared. And if we solve for v, we end up with 34.3 meters per second. Now we also could have done this as a derivation and said that GH equals 1/2 v squared, and bringing the half to the other side by multiplying by 2, then we would have the square root of 2GH. But let's say that there was air friction, and the air friction created a situation where the actual speed was 25 meters per second. So what that means is that instead of speeding up to 34.3, some of the energy turned into heat due to the friction that was created by air pushing on the block. So in this case, we start the same with PEG, but what's different is that right before it hits the ground, the kinetic energy is less. It's going slower because some of that energy turned into work by friction. So we do it the same way. We just can't cancel out the mass this time, 1/2 mv squared. And then we leave that as work done by friction. So we have 2 kilograms times 9.8 meters per second squared times the height of 60 meters is equal to 1/2, again, 2 kilograms. And now it's only going 25 meters per second, plus the work done by friction. Now, if you do this, on this side you get 1,176 joules, and this comes out to 625 joules. So what's the work done by friction? Well, we just subtract. And when you subtract, you get 551. But I'm going to rewrite this like this. Because I want you to see that the total energy that we start with has to be equal to the total energy we end with. So we have PEG, and this time we have less KE, and the amount of missing energy is made up by the work done by friction. Well, what if we wanted to find out how strong that frictional force was? Well, we could just go back and do W is equal to FD. And in this case, that F would be the force of friction. Now, it would be the average force because in actuality, that force would be changing. So we know that the work done is 551 joules, and that's going to be equal to FF times 60 meters. And that gives us an average force of friction of 9.2 newtons. Let's look at a situation where we have a block at the top of a hill. It slides down the hill, but then it goes back up a second hill. And the question is, how fast is it going on this second hill? Well, when it does that, it's speeding up and reaches its maximum speed here, at which point the PEG is all KE. But then when it goes up here, it loses some kinetic energy and regains some potential. So what does our equation look like? Well, it's going to be the PEG that we start with, PEG initial, and that's going to turn into PEG final because it has potential energy here plus the kinetic energy. So that's going to become KE, and I'm going to subtract this to the other side. So that becomes PEG initial minus PEG final. So over here we have 1/2 mv squared is equal to mgh1 minus mgh2. We have m's on all sides, so we can cross those out. And then we can bring the 2 to the other side and factor out the g. So that becomes, once we take the square root, v is equal to 2g h1 minus h2, and then the square root of all of that. If we want to look at something like a pendulum, and we wanted to find out how fast it's going at the bottom, we're going to do basically the same thing. So a pendulum is just a weight on the end of a string that's allowed to swing back and forth. And let's say it's pulled back to a maximum height of h, and then it's released and it swings down. So it starts out with all PEG here, and it ends with all KE down here. So this is basically what we've done multiple times before. PEG becomes KE. We have MGH equals 1/2 mv squared. M's on both sides. Bring the 2 over and take the square root of both sides, and that becomes the square root of 2GH. This is a more advanced pendulum problem. Let's say that we have the pendulum just like before, and it swings down, and we want to know how fast it's going down here. So we want to find V. But this time, rather than giving us H, they give us only the length of the pendulum and also theta. So we want to find this value for H. And the way that we can do that is by making a right triangle. So if we pull this out over here, we can see that with theta and L, the adjacent side with hypotenuse goes with cosine, so this side will be L cosine theta. So now if we look at the string when it's hanging all the way down, that would be L. And then this section here that we just found, the side of the triangle, would be L cosine theta. So this is our H. And H would be the total L, the total length, minus L cosine theta. We can factor out the L and just make that 1 minus cos theta. So now we set it up the same way. We say PEG turns into KE, and we have MGH equals 1/2 mv squared. We don't need the m's. And we can rearrange so that V is going to be equal to the square root of 2GH. But now we have an expression for H. V is going to be equal to the square root of 2 times G times L 1 minus cos theta. So that's how that's done without being given the height, just the angle and the length. Let's look at a collision problem. We know that if we take a ball in the real world and drop it, the ball won't bounce to the same height that we dropped it from. And the reason that that happens is because during the collision, the ball produces heat with the floor. So that heat that's lost prevents the ball from traveling as high. So let's say it only bounces 1 meter high after it's been dropped from 3 meters. How much heat was produced? Well, it starts out here with PEG and it ends here with less PEG. The amount that it lost, that's our heat. So we can start out by saying we start with PEG initial, then we end with PEG final. We know this is going to be less, so what's the amount that we're missing? That's going to be the heat produced during the collision. So if we rearrange that formula, we can say Q is equal to PEG initial minus PEG final. I'm just subtracting this to the other side. So Q is going to be equal to mg, I'm factoring out the mg, H initial minus H final. So when we put the numbers in, we can say, I didn't give the mass of the ball. Let's say the mass of the ball is 2 kilograms. So that would be 2 kilograms times 9.8 meters per second squared. And then we subtract the height. 3 minus 1, so that would be 2 meters. So the heat produced would be 39.2 joules. In this problem, we have a 2 kilogram block on a ramp, and the block is slid up the ramp to the top here. Now, there is friction in this problem. We don't know exactly what the frictional force is, but we know that it takes 15 newtons of force to drag this at a constant velocity up the ramp. So what we can do is we can find the work done to drag it up the ramp. So that's just going to be the 15 newtons times the distance, 50 meters. So when we do the math on that, we get 750 joules. But what is the potential energy gain in this case? Well, let's take a look. We'll put the numbers in and see. So we say that it's a 2 kilogram block times 9.8 meters per second squared, and it's risen a height of 30 meters. And when we do the math, we get 588 joules. So how is this possible? Well, the work to slide it up the ramp gives it 588 joules of potential energy, but it also had to overcome friction. Well, what's the missing amount of energy? That's the heat. So if we take 750 joules and we subtract 588 joules, that's going to give us 162 joules. And that amount of missing energy, that's the Q. This is a tricky problem that comes up on some tests. And what it's asking is, if we launch 3 different balls at 3 different angles from a height of h, which ball is going to land with the greatest velocity? And the question's actually much simpler than you would think. Remember that kinetic energy is a scalar, so the angle has nothing to do with it. If they have the same mass and the same velocity, they have the same kinetic energy. So what's the energy at the top? Well, at the top, they all have the same PEG, and they also all have the same KE. What kind of energy do they end with? Well, they don't have height down here, so they have kinetic energy. This kinetic energy initial is going to be less than the kinetic energy final, but because they must have the same kinetic energy final and they all have the same mass, then the V for all of them is the same. Now, this does not mean that the vertical and the horizontal components are the same. It just means that the resultant velocity must be the same. In this question, we have 2 carts. One that is 1,000 kilograms and we don't know how fast it's moving. And the second one is 2,000 kilograms moving at 10 meters per second. And the question is, how fast must this cart go if it's going to have the same kinetic energy as this cart? Now, if you were doing this as a multiple choice question, you might think, oh, I know, this has to go twice as fast because 20 times 1,000 is the same as 10 times 2,000. That would be the question if you were looking for momentum. But remember, velocity is squared, so that's going to change our answer. So we want to have the same kinetic energy of car 1 be equal to the same kinetic energy as car 2. So all we have to do is do 1/2 mv squared equals 1/2 mv squared. And our mass of our first car is 1,000 kilograms. And we don't know how fast it's going, is equal to 1/2 2,000 kilograms times 10 meters per second squared. And when we do the math on that, you get a velocity of approximately 14 meters per second. So it makes sense that it has to go faster, but it's not double as fast. It's only 14 meters per second. Let's look at this idea of conservation of energy in terms of a graph. So if we have a ball down here, and let's say the ball leaves the ground with some large initial velocity, vi. So as it travels up in the air, it's going to slow down. If it's slowing down, it's losing kinetic energy. But while it's losing kinetic energy, it's gaining gravitational potential energy. So if we were halfway up, it would have lost half of its kinetic energy, but gained half gravitational potential energy. So the total energy would be the same. So what would this look like on a graph of energy and height? Well, when we start out, it would have its maximum kinetic energy down here. That would be Ke max. So the graph would start here. And as it travels up, it would eventually get to the top and stop. So its Ke would become 0. So it would lose kinetic energy all the way down to here. So that would be our graph of Ke. But the gravitational potential energy, it starts at 0, so PEG is 0. And that goes up as it goes up until it gets to the top, and that would be its max. So the PEG graph would look like that. But if we sum them up, 0 plus Ke total, or the middle and the middle, or 0 and the max, that would give us a total energy that would remain the same. That would be our E total. Now, if there was air friction, that E total would actually partially be converted to heat, and that missing amount of energy right there would be our Q. Let's do a power problem. So the question is here, we have a crane lifting a 1,000 kilogram block. It lifts at 10 meters in a minute. And the question is find the power, technically the average power. So the way we're going to do that is we're going to say P is equal to W over T. And we know that power is equal to work, which is force times displacement over time. And the force to lift something is going to be equal to the force of gravity, which is going to be its weight. So that's going to be mg. So that's going to be 1,000 kilograms times 9.8 meters per second squared times the height, which is 10 meters, divided by the time, 1 minute is 60 seconds. So the average power to lift this would be 1,633.3. Do you remember the unit for power? It is the watt. So 1633.3 watts. We'll do one more power problem. This is the other variation that you can see on a test, which is where we're given the distance and the time. So this person pushes this block with a constant force of 100 newtons across the floor. So we can actually find the average velocity by doing V equals d over t. So we know that the distance traveled is 20 meters, and it does this in 10 seconds. So the average velocity is 2 meters per second. Now, we know that power is equal to work over time, and we know that work is force times displacement, and we know that displacement divided by time is average velocity. So all we have to do is do F average V. Well, what's that average power? It's going to be the 100 newtons times the 2 meters per second, which is our average velocity, or the power equals 200 watts. This is a popular question to show up on tests. We have a staircase with two people, and the one person, person A, runs up the stairs in 5 seconds. The second person walks up the stairs in 10 seconds. And the question is, who developed more power? Well, Let's first look at the work done. The work turns into gravitational potential energy. If they have the same mass and they went the same height, then the PEG is the same, so therefore the work is the same. So they both did the same amount of work. But person A did it in half the time, so therefore person A did it with double the power. Depending on how the question is asked, it might be that person B did it with half the power. But in both cases, the work done is the same.